Okay, let us start our lecture. So, in the last lecture, we talked about independent random variables. In chapter 1, we have already discussed about independent events. So we have these two events. Two events, A and B, if they're independent, if probability of both events occur equal to the probability of A times probability of B. All right. So that is for a particular event, a particular two events. All right. So we want to know whether it is the chance that these two events occur at the same time. Then if they're independent, then it's equal to the product of the two probabilities, probability of A and probability of B. If we don't know whether A and B are independent or not, do we still able to compute probability of A intercept B? If we do not, okay, if they are independent, then this is true. But if we have no knowledge whether these two events are independent or not, then how to get the probability of A intercept B? So probability of A and B is equal to probability, do it step by step. So A occur first, and then times the probability of B occurs given that A has occurred. So that's one way to do it. So A happens, and then look at the chance that B will occur if A has occurred. Or alternatively, you can look at B first, and then A given B. All right? So these two ways do not require A and B are independent. All right? So it applies to independent and not independent events. Now, but then when we come to the random variables, when we say two random variables are independent, and this is a very strong statement. Why? Because you can think of it like this. Let's say X takes two values. X can take value 1 and 2 with probability, let's say, 0.4 and 0.6. All right? So this is a random variable, and this is the distribution of X. And then Y, let's say the value takes the value 2 and 4, or 2, 4, 6, and the probability is 1/3, 1/3, and 1/3. All right? Okay. Okay. In fact, this is not. Okay. So what I want to say is that an event can be X equal to 1. This is an event. Or X equal to 1 or X equal to 2. This is another event. Or you can consider as this event union this event. So my point is, when we talk about random variables, there are many events behind. So when we say independent random variables, so that means there are a lot of events behind these two random variables. So that's why when we talk about two random variables, all right, they are random variables. And we say that if X and Y are independent, then we have this joint probability density or probability function equal to the product of the two marginals. Not only that, it has to be valid for all the xy. for all xy. Any possible xy. That means it basically look into all the possible events, joint event, and the probability of this joint event is equal to the product of the two marginals. All right. So it's a much stronger statement. When we talk about two independent random variables, it's stronger than just saying that two events, because a random variable can take on many possible values, and each of these one can be considered as one event. All right. So we in the last lecture we talked about an example. Here is an example. All right. We are given the joint PDF of x and y, and from there we can check whether xy are independent or not. So you can check whether the joint distribution equal to the product of the two marginals for all the xy. All right. Is it true that how about what is this value? The probability function. Evaluate x equal 3 and y equal 4. What is the value? So x equal to 3 is not here. Y equal to 4 is not here. So this is 0. All right. On the other hand, what is f of x3? So x takes the value 2 with probability 0.4, takes the value 4 with probability 0.6. Therefore, this is also 0. So f of y, evaluate at 4, similarly, is also 0. So, in other words, this f of xy equal f of x times f of y also holds for any other values, not given in the table. All right? So, it's true for, this relationship is true for all xy values. Then they are independent. All right? So now let's look at another example. In this example, we have joint distribution given in a functional form. Functional form, x times y over 36. All right? And this formula for the PDF applies to x equal 1, 2, 3 and y equal to 1, 2, 3. All right? So in other words, how many possible values are there for which this functional form of the joint PDF can be used or can be applied? All right. So for x equal to 1, y can be 1, 2, or 3. For x equal to 2, y can also be 1, 2, and 3. For x equal to 3, y can be 1, 2, and 3. So altogether, there are 9 possible values for which we can apply this formula for the joint PDF. Then, for any points outside these 9 possible values of xy, the PDF are 0. All right? So just I keep telling you that for joint PDF, remember whether each of these is bigger or equal to 0. So outside this range, of course, is 0. But then with it, this two specified range for x and y, this is also bigger than 0 because xy are positive. So the only thing that you may need to check is that whether the sum of the joint PDF over these two range, x equal 1, 2, 3 and y equal 1, 2, 3 equal to 1. All right. Although you are not asked, the question that we are asked is whether xy are independent. All right. But let's assume that this summation, if I write it explicitly, it will be Sxy 1, 1 plus f of xy 1, 2, and so on. And the last one is f of xy 3, 3. All this, whether it's equal, end up equal to 1. It should be, otherwise it's not well defined. To write it down as in a mathematical form, it simply means that we are summing up the joint PDF, which is this, when y equal to 1 to 3. All right, so that means the subscripts y change from 1 and then 2 and then 3. And for x equal to 1 to 3. All right? So in other words, now this double submission sign to some of you may be quite complicated, but what it means is that, okay, first of all, we start from the outside, the most outer summation sign, so this x equal to 1 to 3. So in other words, we take x equal to 1, x equal to 2, and x equal to 3. Okay, then for x equal to 1, now you try to look at, okay, you can write it like this. This basically simply means that x equal to 1 to 3, and when y equal to 1, it means x times 1 over 36 plus x times 2 over 36. This is when y equal to 2 plus x times 3 over 36. This is what it means by this summation. All right? We just change, we have the general form, x times y over 36. You just change the y value from 1, then you have one term, y equal 2, another term, y equal 3, the third term. Do we have y equal 4? No. Why not? Because this, what we are given is that the John PDF takes this form only when y takes value 1, 2, and 3. So no y equal 4 in this case. All right, so just make sure that it's equal to 1. But you don't have to verify it unless you are asked to verify it. Otherwise, you just take it as the sum equal to 1. All right, it's well defined, unless they're type polar. All right, okay, so now, how to get the independent? So we just learned that in order to show that these two are independent, what we need to show is this holds for all xy, x equal to 1, 2, 3, and y equal to 1, 2, 3. All right? So we have to show this is true for all x equal to 1, 2, 3, and y equal to 1, 2, 3. So in order to work out this one, we need to know what is f of x. So I try f of x. So f of x, you just have to fix x and then try to add up all the, so basically if you recall, the marginal is equal to sum over all the y's of f of xy. All right? But this John PDF is equal to 0 for other possible y values. So basically, it's equal to sum y from 1 to 3, xy over 36. Okay, for other y value, this John PDF is equal to 0. For other y values, such as 4, 5, 6, no, the John PDF is, the John probability function is 0. So it boils down to this one. So that's how we got this one. Now the general term is x times y times 1 over 36. So in other words, every term in this summation, how many terms are there? 3 only, because y takes value 1, 2, and 3. So 3 values, and these 3 values, or 3 terms, each of them have something in common. 1 over 36 is there. X is there. All right? Each term will have this 1 over 36 times x. So I just bring out this factor, which is common to all these 3 terms. We call this common factor. So bring it out of the summation sign. So now we just basically sum y, where y takes the value 1, 2, and 3. So just add up 1, 2, 3. So it's equal to 1 over 6. 6. So 6 over 36 is 1 over 6. All right. And this, the way that we do it, all right, applies to all the x value equal to either 1, 2, or 3. But it will not apply to x equal to 4, 5, 6, and so on. Because the John PDF in that case is not xy over 36, but 0. So it only valid for x equal to 1, 2, 3. All right. So we do the same thing for the y and get the same answer or similar answer. So now I got f of x and I got f of y, and I know the range for which one this marginal probability function is valid. So now I check. All right. So f of xy equal to 1 over this 6 times xy, and f of x is x over 6, and f of y is y over 6. And this product is equal to this one. All right. So f of xy is equal to f of x times f of y for all the xy equal to 1, 2, 3. Now this means that in the equality sign, there are two, on both sides of the equality signs, there are a bunch of numbers. So this xy and this side is 1, 2, 3, which means that x can be 1, 2, 3 and y can be 1, 2, 3. All right. Does this mean that x and y has to be the same? All right. My question is whether I can only take this value. No, it simply means that x can take 1, 2, 3. Y can also take 1, 2, 3. And I did not say anything about x equal to y. So x and y can take any values so long as it's 1, 2, 3. All right, so long x and y takes value 1, 2, 3, then this statement f of xy is equal to f of x times f of y. All right. So x, y are independent. Okay. Okay. So now I have this xy and they are independent. And in fact, f of x is equal to e to the power minus x for x bigger or equal to 0, and f of y equal e to the power minus y when y bigger or equal to 0. So now we are asked, what is the John PDF? All right. So in general, in fact, I mentioned many times, for two random variables, x and y, if you are given the John PDF, then you know everything about the x and y. You can compute the probabilities related to x, related to y, or related to x and y jointly. And you can compute the conditional or the marginal distribution of x, marginal distribution of y, and also you can compute the conditional probability of y given x or x given y. So all this will be computed, and you should know how to compute or to get all this, all right, from a John distribution. Whether it is discrete or whether it's continuous, you should know how to do it. Then, now the question is, okay, if it's not given to us, are just given partially f of x and f of y. That means the marginal distribution of x and the marginal distribution of y. Can we get the John probability function or probability density function? In this case, it's a density function because x is continuous and y is continuous. How do I know x is continuous and y is continuous random variables? Because the range for the functional form of f of x and f of y to be valid is over a region, over the positive real line. All right. Take uncountably infinite many values. So they are continuous. Okay. So now we are only know a part of the information. We know about how x behaves, how y behaves. So can we get the John probability function? So the answer is no in general. All right. Given these two, to get this one is not possible. If you want this one, what you need is you need this and what else? We need this. All right? The margin of x times the condition of y given x. Or the other way around, f of y times f of x given y. Okay? So this holds for any situation. All right? But if we don't know the conditional distribution, all right, then we'll be not able to do it. But in this example, we are given a very powerful information, very strong information. It says that x, y are independent. Because of this independent properties, then the John PDF is just the product of the two marginals. The product of two marginals. So we just multiply them. All right. So the distribution, the John distribution is equal to e to the power minus x times e to the power minus y over the region x bigger or equal to 0 and y bigger or equal to 0. Always remember when you talk about this John PDF equal this expression, you must specify the range for which this is valid. So here it is x bigger or equal to 0 and y bigger or equal to 0. So you can think of it like this. This is x, this is y. So for this f of x is over this line. So we talk about how it behaves. And for y, we talk about how this behaves. All right. So the John PDF will be valid over this region. All right. Which is just the product of f of x and f of y. Okay. So I simplified it. So it's e to the power minus x plus y. Okay. Now, let's look at this example. Suppose we're given the John PDF. The John PDF is equal to this expression when x is between 0 and 1 and y is between 0 and x. Now, it's very, very important that you have to figure out the region for which the John PDF is given by this expression 2 times x plus y. So it's over this region. All right? Over this shaded part. How do we know that? So there are 4 inequalities. X bigger than 0, x less or equal to 1, y greater than 0, and y is less than 1. This is the line y equal to x. All right? So it's bounded by these 4 inequalities. And it turns out this as a triangle. All right? So, are x, y independent? All right? So we do the hard work. Means that we have to work out what is f of x and what is f of y. And also specify this one is equal to that particular expression over certain region of x. I believe it is x between 0 and 1, and this is y between 0 and 1, equal to certain expression. All right? And then we check whether the product of these two equal to f of xy. Over this region and this region. All right, so let's look at f of x. So f of x, so we do the integration. So in other words, if you go back to this, I want to figure out what is the behavior of x. So I have to integrate all the y's. That means I have to get rid of the y. So for fixed x, all right, so I'm looking at integrate, all right, from y from 0 up to y equal x over this region, over this interval. So I integrate y. This is y from 0 to x. All right? And this is valid for x between 0 and 1. Why? You think of it. So my integration is for fixed x. I integrate. So I try to squeeze all the density at this point. Squeeze all the density here at this point. So after I squeeze all this, then all the density will lie on this line. So it's from 0 to 1. Outside that range, outside it, all right, this part onward and this part onward, there's no density. Okay, that's what it means. So we integrate. So this is equal to this integration, or the f of x equal to this when x is between 0 and 1. So, so for those who are not familiar with how to do the integration, this is just integration of one variable, although you see x and y in there. But just remember, we are trying to integrate with respect to y. Therefore, x, you can treat x as just a constant. All right, it's not number, but it's just a constant. It won't change the value. All right, then we just integrate with respect to y. So that's why this becomes x times y when you integrate. So x times y squared over 2. All right, then substitute y equals 0 to x, and we have this 3x squared. All right, when x is between 0 and 1. Okay, make sure that your fy will not see any y there. If you still have a y there, something wrong with your integration. All right. F of x, the density function of x, should not involve any y. But the same is not true for this one. Huh? The conditional distribution of x given y is a function of x. Also, it may be, also you may see a y there. All right? Because it also depends on y. All right, so I do the same thing for y. Now for y, I have to integrate x. So if I go back to the picture here, okay. So what? This is the region, right? For which the PDF is non-zero. So I integrate for fixed y. I have to integrate out x. So x at this point, x is equal to y. At this point, x equal to 1. Therefore, my integration is to collect all the density over this part and put it here. So my integration is from x equal to y up to x equal to 1. And after I complete everything, all right, so the density will be on over this part. It's from 0 to 1. Outside it, because there's no density, so even if you collapse it, it's still 0. So 0 otherwise, when y is not between 0 and 1. So we just do the integration, and it turns out that, it is 1 plus 2y minus 3y squared, when y is between 0 and 1. All right? Then the f of xy is equal to this over this region. And f of x equal to this times this, when x is between 0 and 1, and this is equal to this when y is between 0 and 1. Is it obvious that f of xy does not equal to f of x times f of y for some xy. All right. Now, I have to stress that if you want to show that they are independent random variables, you have to prove that f of xy equal to the product of fx times f of y. Not just for one point, just for one particular xy value, but you have to show that it is true for all x and y. All right. But while for dependence, so long as you can find one point, one xy, such that f of xy does not equal to f of x times f of y. So in this case, we find that, all right, any points, okay, that make it, okay, maybe x, let's say x equal to 0.5, xy equal to 0.5 and 0.5. So it falls here and here. So the product of f of x and f of y will be 3x squared times 1 plus 2y minus 3y squared. For this particular point, the product of f of x and f of y is given by this expression. Is this equal to 2 times x plus y? Obvious not. So x and y are not independent. Am I clear? So, okay. This already show, but then I want to make it more concrete. I just take one point. Okay, can I take the point 2, 2? Yes, but then it won't help because 2, 2, what is f of x at 2? It is outside this range, is 0. So therefore, f of x is 0, f of y is 0. And f of xy is also 0. So it does not help. All right. Let me go back to this one. All right. So if you take a point, let's say 2, 0, 2. 0, 2 is here. 0, 2. X equals to 0 and y equals 2. Then what is f of xy? It is 0. All right. Then what is fy? Is 0. This is okay. Fx0 is questionable. All right. Maybe I should use the biology like 2, 2. 2, 2 is somewhere here. I mean, outside the range. All right. But this f of x, f2, 2 is 0. Fx2 is 0. Fy2 is also 0. So it holds. This f of xy equal f of x times f of y. So it won't help. All right. So what I'm trying to look for is something. So let's say I take this point 5 and 5. All right. Then the marginal distribution of f of x is given by that. F of x. This is the point f of x. All right. They have non-zero density. F of y is also have non-zero density because you have this part. You add up, put it here. So both f of x and f of y at 0.5 are non-zero. But what is fxy? The joint distribution. At this point, it's outside this range, so therefore this is 0. So they are not the same. But I don't know whether you accept the more general arguments. How can this product of these two equal to this? You multiply two factors. One factor involves y squared. How can the product, all right, is the same as the term with only 2 times x plus y? No y squared there. So of course, it cannot be the same. All right? Okay, so that shows that x and y are not independent. So let me repeat it again. So in order to show x, y are not independent, our job, in fact, is very easy. If you are able to find one particular point, x, y, such that the f of x, y does not equal to f of x times f of y, then the job is done. For independent, it's much harder. You have to check f of x, y, the joint PDF, equal to the product of f of x times f of y, not just for one point. It's not good enough. You have to check it for all points. All right? So any point that satisfies this and this, all right? Any points between x, between 0, 1 and y between 0, 1, then the product of f of x times f of y does not equal to the joint PDF because one of the factors involves y squared, while the joint PDF does not have any y squared. How you create a term with y squared? No, you cannot. All right, but in fact, okay, this is what. This is the point that I take. X equal to 0.6 and y equal to 0.8. Then you show that the joint PDF does not equal to the marginal product of the marginals. All right. So in fact, with this one, I really compute the density. F of x is 1.08. F of y at y equal to 0.8 is 0.6. And the product of these two numbers does not equal to this. And this is 0. And why is this 0? It's given because point is not in the region for which the joint PDF is equal to 2 times x plus y. Because this is outside the region. This point outside the region. So at least for this point, f of xy does not equal to f of x times f of y. So xy are not independent. So I just showed you, make sure that you know it is not independent because I find one point, at least one point, that this is not true. This is like that. All right. In fact, I don't know whether you noticed, whenever the John PDF, all right, is valid over a non-rectangular region. Non-rectangular region. So in this case, it's valid over a triangle. All right. Then that means that you can always find one point which the John PDF is 0. Like in my example, I take 0.6 and 0.8, or just now I take 0.5, 0.5. All this point with the John PDF equal to 0. So the idea is like this. I take this point. Obviously, the John PDF is 0. But then this point, the f of x that is here, I mean the f of x, you can consider you sum up all the density here. So it's non-zero. Similarly for the y, because this part you sum up is also non-zero. So the product of two non-zero values cannot be 0. Therefore, it must be dependent. It cannot be independent. So one criteria that x, y are independent, all right, is that the space for which the John PDF defined has to be rectangular, or we call it product space. Product space. All right. So in other words, if f of x is valid over 0 to 1 and f of y is valid equal to 0 to 1, then your John PDF must be equal to that expression over this unit square, x between 0, 1 and y between 0, 1. That's, we call it product space. All right. So if it's valid, f of x is valid over this, f of y equal to something when y is between 0 and 1, then we need to look at f of xy equals certain expression over this region. We call it product space. And this is multiplier times. So basically, it is the length x between 0, 1 and y between 0, 1. The product space is the rectangle. Right. And in this case, because they are equal width, so it's a square. It's a square. All right. And so in other words, if f of x in this example, I think here is 2x plus y, but this formula does not apply to this. It only applies to this part, which is a triangle. So obviously it's not independent. Because the witness is that you can take a point outside this triangle, which is still in this unit square, for which f of x is non-zero. F of y is non-zero. But while f of xy, the John probability density is 0, how can you find, how can the product of two non-zero numbers equal to 0? So therefore, the John PDF cannot be the product of the marginal. So so we find that a point that this does not hold. So xy are not independent. So in other words, it's very easy. If you look at your John PDF, I don't have to do all this f of x, f of y. Look at the John PDF, which is like this. John PDF valid over this region. And this is not a rectangle. It's not a product space, not a rectangular space. Then it is not, the two random variables are not independent. And the logic is very simple. Because I can find a point for which x is valid, f of x is non-zero, f of y is non-zero, but f of xy is 0. All right. So to make it so it's like this. All right. So if f of x is defined over this region and f of y is defined over this region, so this is the product space. If my John PDF is defined only over this range, then obviously then xy are not independent, because here there's some point here for which the John PDF is 0, while the marginal of x, because we have this part, we have all density here, so at this point the f of x is non-zero. For this bond, y at this value is non-zero because we have density over this part. So f of x is non-zero, f of y is non-zero, but f of xy is 0. So therefore, xy are not independent. So this product space is very important to find. If you don't have product space, then it's not independent. But if it is product space, we may still have the case that xy are not independent. So here is example 5. All right? Example 5, I give you the John PDF. This one is okay. Okay, I think it's example 6. Okay, now I give you another example. John PDF is like this, over a rectangular space. All right? X between 0, 2 and y between 0, 1. So you can see that this is a product space. All right? The range for which this John PDF defined is over a rectangular region. So are xy independent. So in this case, I try to work out. So I skip the detail, leave it to you. So f of x turned out to be half times x, where x between 0 and 2. And f of y, after complete the integration, is 2/3, 1 plus y, when y between 0 and 1. So therefore, f of xy is equal to f of x times f of y, for x between 0 and 2 and y between 0 and 1. So xy are independent in this case. All right, so, but how about this one? Example 6. I look at it. So, is this a rectangular space? Right? Yes. Why? Because the region for x, it does not depend on y. So it's just between 0 and 1 for x. How about y? Y is also between 0 and 1, right? This one, this one. So the John PDF is defined for any points within this product space. X, y between 0, 1. All right? Then are x, y independent? And so we try to get f of x, get f of y. So left it to you. I have already done it. So you just follow. So f of x equal to x plus half, where x is between 0, 1, and fy is between equal to 1/2 times 1 plus 3y squared, when y is between 0 and 1. So now, you can see that, recall what is f of xy. F of xy is equal to this. Okay, x plus 3 over 2y squared. So, this is x over 2 plus 5. X over 3 times 2 plus y squared, right? Okay, x plus 3 over 2y squared. X plus 3 over 2y squared. All right? But while this one, f of x is equal to x plus half. X plus half. And then y is equal to, f of y is equal to half times 1 plus 3y squared. Half times 1 plus 3y squared. So how can the product of x plus half and half times 1 plus 3y squared equal to this one? All right? F of xy is equal to x plus 3 over 2y squared. F of x is equal to x plus half. And f of y equal to half 1 plus 3y squared. So how can the product of these two equal to this one? You know that it cannot be, right? You multiply f of x and f of y will not give you the expression in the f of xy. So they are not independent. Right? Is it obvious? Right? It is quite obvious because if you multiply the two, you will have a constant 1/2 times 1/2 times 1. But there's no constant term over here. Okay, only two terms. One involves x, one involves y squared. So it cannot be the same. All right? So this is through the standard procedure. Given my joint PDF, I look at f of x, look at f of y, and then I find out that f of x, y, the joint PDF does not equal to the product of f of x times f of y. Right? Okay. Now, but I have an easy way. So, see, I don't want to find f of x. I don't want to find f of y. I just mentioned it, so don't worry about if you don't get it. Okay, look at that joint PDF. If I can factorize the joint PDF into product of two things, one factor involves only x. The other factor involves only y. Then, if I can do that, also I have to check the region, whether it's a product space. But at least I check the form, the formula first. The joint PDF, if it is the product of two factors, all right, one involves only x, the other involves only y, then it's likely that they are independent. Of course, remember to check the region for which this is valid. That means check whether the joint PDF is defined over a rectangular shape. All right. If it's not a rectangular shape, then there's this loophole that you can find a point. The joint PDF is 0, while the marginal of the x and margin of y is non-zero. Okay, so can we factorize this into 2? Can we write this as x and the other one is like that? I factorize, this is the sum of two terms. Factorize means that this times this. Okay, so we cannot factorize into two parts. Let's go back to the previous examples that we discussed. Let's say example 5. Our answer is x, y are independent. Look at this one. Can I factorize it into two factors? Right? One is this, the other is this, right? So it's the product of these two. Okay, so let me go back to what is f of x? Oh, half x. Unfortunately, this is not half of x. It's okay. You want half of x? Okay, half of x. Then in order to get 3 over 2. That means this one, I rewrite it as the product of 1/2 x, right? And 2 over 3, 1 plus y. All right? So, the first factor is f of x. The second factor is f of y. But we don't need to know what is f of x, f of y, so long as we can write it as a product of two factors. I can write it like this. Okay, this is not f of x, this is not f of y. But if I can write it like that, all right, then f of xy is, x and y are independent random variables. All right. So if you're asked to prove, okay, since this is not in the notes, it's just you have to work out where f of x, f of y, things like that. All right, but you can check, use it as a check whether the product space is valid for the joint PDF. If the joint PDF is the formula for the joint PDF is not over a product space, but over a region which is not a product space, then it is not independent. Then if f of xy can be written as the product of two factors, one involves only x, the other factors involve only y, then x and y are independent. Okay, so, all right. So now we move on to talk about expectation. We discussed this for one random variable case. So now two random variable case. So we start with a function of xy. Is it a function of xy? Is this a function of xy? Huh? Is this a function of xy? Is this a function of xy? Is this a function of xy? Yes or no? Yes. Yes. Is this a function of xy? Yes. So that means no matter what your xy values are, always have the image equal to 3. It's a function. Function is that you map any xy point and get some values, all right? Some value, some real numbers. So you can have all the xy point mapped to one point, all right? So this is a very general situation. So expectation of a function of xy is equal to that particular function times the corresponding probability function or probability density function, and then sum over x, sum over y, or integrate over x and then integrate over y. All right? So that's just compare with the one variable case. Expectation of g of x is equal to sum of g of x times the density function or the probability function over x. All right? The function times the PDF or probability function. So in particular, this one. So gx is x, so it's x times f of x. All right? So that is the expectation of x. And x squared, if gx equal to x squared, then that is the expectation of x squared, and so on. But now we just extend it to a function of x and y. So since it's a function of xy, so you need to know the John PDF of x and y. All right? Knowing just x, the probability function or probability density function of x is not good enough for you to compute the anything expectation of xy, gxy. All right? You need to know both. All right. So a special case is this. X minus mu x times y minus mu y. What's mu x? Mu x is expectation of x. Mu y is expectation of y. So the idea is that, okay, let's look at how, right? You can think of it like this in a two-dimensional plane. So this is mu x, the point mu x and mu y. All right, mu x is a number, mu y is a number. So mu x, mu y represent a number. So this is my particular point xy. xy. So basically I'm saying that, okay, let's look at the difference between x and mu x. So in other words, this is the part. Mu x, the difference between x, this is the x coordinate. And this is the mu x coordinate. So look at the difference of this. At the same time, I also look at y and mu y, the difference of y. So this is y, and this point is mu y. All right. So we look at x, the difference between x and mu x, and mu y. For the same point. Now, suppose I can only give you, suppose all my points are like that. All right? Then the mu x, mu y may be, let's say, somewhere here. Mu x, mu y. So you can see that, for example, this point. Now this point is less than the mu x for the x coordinate. This point that I just circled is less than mu x. At the same time, y, the y value of that point, is also less than mu y, right? So in other words, the product of x minus mu x times y minus mu y will be positive. Similarly, for this point, remember this is my mu x, mu y. So this point, the x value is bigger than mu x, and the y value is also bigger than mu y. So the product of x minus mu x times y minus mu y is positive. So the expectation of this quantity is that, okay, the idea is like this. How likely, if this point, all right, how likely this point, so basically the expectation, okay, the expectation, it simply means that you have to evaluate this. This is the function, evaluate at the John PDF, and then for discrete case, take expectation means that you sum over x, sum over y. So if it behaves like this, then this quantity is positive because they are of the same sign, basically these two factors. All right? Then times the weight and sum them up. So basically, you just try to look at whether the xy are positive correlated, which means that if one variable is above the mean of x, x is above mean of x, it's likely that the corresponding y value is also above the average, above the mu y. All right? And if the point x is below mu y, mu x, right, like this point, all right, then the y is also below mu y. All right? So that's one way to look at it. Think of it. If the points are like that, so suppose this is the point mu x, mu y. So look at this point. The x value, is it bigger or less than mu x? Less, right? It's on the left-hand side. So x minus mu x will be negative. Then how about the y? This point, the y value is below or above mu y? It's above. So y minus mu y will be positive, while x minus mu x will be negative. So the product of x minus mu x and y minus mu y will be negative. Similarly, for this point, this time the x minus mu x is positive, while y minus mu y is negative because this point is below mu y. So the product is negative. So if you have the observations or the data look like this, then the correlation is, not correlation, the covariance is negative, which means that if x is above mu x, then it's likely the corresponding y values will be below mu y. That means the xy are behaved in a different direction. So if x is above mu x, then it's likely y is below mu y. On the other hand, if x is below mu x, then y is above mu y. So that's what, when it is negative, when this is negative, when this expectation is negative. That's how we interpret it. All right. So basically, to summarize, this quantity is measure how xy behaves. So if they go in same direction, then this covariance or this expectation should be big, a positive number. All right? If they go in different directions, then this covariance will be negative. Will be negative. All right? So for discrete case, it's equal to this. For continuous case, you have to do the integration. All right, so here is just some of the properties about this quantity called covariance. Covariance may be, we use it less frequent, but another quantity derived from this covariance is something called correlation coefficient. You must have heard about that. Correlation coefficient between two random variables. Okay, we'll discuss it in a few minutes. But okay, about covariance of x, y, it can be shown equal to expectation of x times y minus mu x times mu y. It's similar to this. If you remember, we have this formula, right? It looks very similar, except that this is for one variable case, one random variable case. Now this is for the joint random variable, two random variable x and y. It's equal to the expectation of x times y. This is a function of xy. Are these two the same? They are not the same. Okay, we can prove that, but then at least you have to understand the first one, or this one, means that you are talking about a new random variable, which is the product of two random variables, x and y. And in this new random variable, xy, I want to find the expectation. All right? Well, this is obvious, this expression. It means we have this random variable x, and we find the expectation of x first, and then we have this random variable y, and then we find the expectation of y. All right? And then we take the product of the two. And in general, these two are not the same. So my point is, the first one, you multiply, do the multiplication first. All right? Of two random variables, multiply two random variables. This creates new random variables. And then the next step, you take the expectation. And in general, you cannot switch the order. Take the expectation first of x and expectation of y, and then do the multiplication. No, in general, they are not the same. That means this multiplication and the expectation are not communicated. You cannot, must follow the order. You cannot swap the order. But is this true? Is this true? This one is, what is it? Okay, on the left-hand side, it is adding, get a new variable, which is the sum. You do the addition first of the two random variables. After that, you take the expectation. Now I asked, okay, now can I do the expectation first before I do the sum? Expectation of x and expectation of y, and then do the sum. Is it correct? Is it okay? Wow. 2 days before the midterm test, and you don't. Is it correct? Expectation of x plus y equal to expectation of x plus expectation of y. Either you're too busy for your other test, you have not prepared your help sheet. Yes. So addition, okay. Multiplication, not okay. All right. Am I right? Huh? Oh, I'm the only one saying that expectation of x plus y equal to expectation of x plus expectation of y. I'll check your notes. Okay. Anyway, in fact, you can see if I write down expectation of, covariance of xy is equal to expectation of xy minus, this is, in fact, this is the same as this one. This is what we mean by mu x times mu y. So these two are not the same. So if they're always the same, then we don't need to talk about covariance of xy. Why is bother to talk about covariance of xy? These two are not the same in general. Then, of course, is it possible that these two are the same? Under what conditions? When x, y are independent, then they're the same. They're the same. So what does it mean? It means that if x, y are independent, then the covariance of x, y is equal to 0. All right? Let me repeat it. We can show that if x, y are independent, which I don't want to do it here, if x, y are independent, then expectation of x, y equal to expectation of x times expectation of y. In that case, the covariance of x, y is equal to 0. All right? Now remember what I said. I say x, y are independent then the covariance of xy is equal to 0. Not the other way around. Huh? If covariance xy equals 0, does not mean that xy are independent. X and y are independent. This statement is a very strong, powerful statement. Your covariance equals 0, or covariance of xy equals 0. It's only a very small statement. It's just not that powerful. Okay, so if xy are independent, then the covariance is 0. But covariance is 0 does not mean that xy are independent. All right. Okay. Then, that's what I said, right? And then, these are something that you can prove algebraically. But basically, it's just saying that, okay, if I change the variable by adding a constant to it, it won't change the covariance. Only multiply a constant to the random variable. Then the covariance will be multiplied by that same constant. All right? Now, if you find it hard to understand, this is simply saying that if I have covariance ax and y, then this is equal to a times covariance of x and y. All right? So it's like that. So that is the basic ingredient. And covariance of x plus b and y is the same as covariance of xy. Adding a constant will not change your covariance. It all can prove, all right? You just try to evaluate this. Follow the definition of covariance between two random variables. And then you will find that adding a constant will just get rid of. I mean, it will cancel out, so it will not affect your covariance. But multiply a constant factor, it will change the covariance. All right? Then you combine these two, so you get covariance of ax plus b times y, and y is equal to a times covariance of xy. Okay, so at least we do one part. Then now I change the y to cy plus d. So it's the same thing. So that's how we get all these properties. So variance of ax plus by. This in fact summarizes a lot of things. So if I have a random variable, which is the sum of ax plus by, then the variance, this is the variance, is equal to a squared times variance of x and b squared times variance of y plus 2 times ab times covariance of xy. Why is that so? I just give you some idea. All right. So basically, if you recall, what's variance of xy? So it's expectation of ax plus by minus the expectation of, right? Expectation of this whole thing is equal to a times expectation of x plus b times expectation of y. So I just minus the expectation of ax plus by. I write it like that, and square. All right. That is the definition of the variance. So I group this as ax minus expectation of x plus b y minus expectation of y. All right. So it's just like that. Okay, maybe you lost already. Just give you one idea why we have this one. Just let me ask you. Let's say m plus n squared. Does this equal to m squared plus n squared? Is it true? Is it true? No! We have this cross-product term. All right? So this part comes from the cross-product term from the definition, because variance is the expectation of a square. So when you expand the square, you have this cross product term. That's why you have this thing. All right? This is to deal with the cross product term. All right? Okay. So under what conditions this term disappears? So go back 2 steps. So what happens when covariance xy equals 0? When xy are independent. So when xy are independent, wow. Yeah, so it happens. So we don't have the cross product term. All right? So when xy are independent, this one equals 0. So we don't have these terms. All right? But only when xy are independent, then you have this nice property. So you see why we loved independence. If xy are independent, you see, even the variance of this ax plus by suddenly reduced to just a square variance of x times plus b squared times variance of y. Right? Let me confuse you further. MMO, right? O is MMOP. How many terms are there when you expand it? So you have m square, n square, p square, and you have 2mn, 2mp, 2np, right? So if independence, then I can get rid of all these covariance terms. I mean, right? If I talk about the expectation, then I have a bunch of things there. So I can get rid of those if they're independent. Okay, right? How about if I have 10 terms, m1 plus m2 plus mn, m10 square. You know how many terms are there when you expand it? How many mi square? m1 square, m2 square, m3 square, up to n10 square. How many cross product terms? Hey, you should know, this is part of the combinatorics that we learned in chapter 1. We basically just took any 2 out of how many? 10 of them. So you choose 2 out of 10. How many are there? 2 out of 10? 10 times 9 divided by 2. 45. Wow. 10 m square, mi square, plus 45 cross product terms. Totally 55 there. I have to find expectation of all these 55 terms involve variance of m1 and then also covariance of mi, mj. If they are all independent, then I can forget about the 45 cross product terms. All right? So that's why I love independence. All right? And you should also love it. It makes life easier. Okay, correlation coefficient. It is defined as the covariance of xy over the square root of variance of x and square root variance of y. Now, I want you to appreciate that when something called coefficients, okay, let's put it this way. I have xy, all right, the covariance is equal to 100. I also have a covariance of, let's say, w and z, and the covariance equal to 100,000. Wow, one is 100, the other is 100,000. So which one has a larger covariance? Can we compare them? All right. Basically, covariance is measure how the behavior of the 2 random variables, how they behave jointly. So the magnitude of the covariance depends on how the degree of association between the 2 random variables. But this is not the only factor. It also depends on the magnitude of the x and y. If x, y are of small magnitude, while w and z are of bigger magnitudes, right? Just like you hold a $1, we don't have $1 note, a $2 note, right? Sing dollars, right? If you go to South Korean, right, the won, right, the note start with 1,000. Wow, holding a note is 1,000, while we are holding a $2 note, Singapore dollars. Which one is more value? I don't know. Okay, it is the $2, if I'm not wrong. But what my point is, yeah, you're holding a 1,000 won note, and I'm holding only $2 note, a 2, only the value is 2. But you cannot look at it like that, right? So my point is, the covariance is affected by the magnitude of x and y. So we try to adjust the magnitude. So how to adjust it? Naturally, we will divide some number, which tells you the magnitude of x, magnitude of y. So which one can tell you that? So we use the standard deviation of x and the standard deviation of y. All right? Standard deviation of x and standard deviation of y. So we divide it by that, and we can show that after you divide it, it's so nice that everything will be between -1 and 1. Remember, the covariance, in fact, is from minus infinity up to infinity. And minus means that they go in opposite direction. If positive, it means that they go in the same direction, in the sense that if x is above mu x, y is above mu y, then we say that they go in the same direction. Opposite direction is if x is above mu x, y is below mu y, or x below mu x, y is above mu y. All right? So that is how we interpret it. So now I adjust by standard deviation of x and standard deviation of y, then this number, we call it correlation coefficient, is between 1 and -1. So this is a very useful quantity to measure the degree of association between two random variables. So we measure the linear relationship between x and y. And if x, y are independent, then the covariance is equal to 0, which means that the correlation is equal to 0. Because now the numerator is 0, your denominator is the standard deviation of x and standard deviation of y, they are non-zero. So the correlation is 0. And same thing. Correlation 0 does not imply independence. Okay, let's look at this example that we did it before. And we work out expectation of y minus x. Find the covariance of xy, find the correlation coefficient, and find the expectation of y given x equal to 1. All right? So, now this one, I use the method is sum over xy, g of xy times the PDF, the probability function. So this is what I did here, right? This is a function of xy. All right? So I got it, the answer is 1. But alternatively, as I said earlier, expectation of y minus x is equal to expectation of y minus expectation of x. So long as, okay. Is this correct? Is this correct? If you have hard time to understand it, x times y is a product of two random variables. So again, it's a random variable. So basically, this is a random variable. All right? If you call it, you can call it v. So it's expectation of v plus sub u. So this is correct. But this one not equal to, this is wrong. All right? Because this one does not equal to expectation of x times expectation of y. All right? So you have to aware of. Okay, so this is expectation of y and expectation of x. So it's equal to 1 again. And how to get this? There are two ways to do it. One is to get the marginal of y. Then multiply y and sum over y. Right? Of course, you need to work out this part. But what is the second way? Y treat it as a function of xy and multiply the John PDF of f of xy, sum over y, it's better sum over x first, and then sum over y. And why I have to do that? Because in that case, I can bring out y, because I'm summing over x. So y is the same throughout all this first summation. So I can bring y out. So basically this is sum over y times summation f of xy, sum over x. What do we call that? Do you recognize that? That is the marginal of x. Your John PDF sum over x. That means you fix y and sum over all the density or probability function with the same y value. So that is the marginal of x. All right? So, marginal of y. I'm sorry. Marginal of y. Sum over x, so it's marginal of y. Okay, so that's the answer. So my point is that there are many ways to get the answer. So you have to know, if possible, know more than one way, so that you understand that they are all the same, will get you the same answer. All right. Then for part B, the covariance. So for the covariance, we first of all find the expectation of x times y. So this is x, y, then times f of xy. All right, so it's 0, 0 times f of xy evaluate at 0, 0. Then x equals 0, y equals 0. So this is f of xy evaluate at x equal 0 and y equal to 1, which is 1/4. And so on. Oh, wow, seems 1 is a lucky number. It appeared a 1 again. Just now expectation of y minus x is also 1. So expectation of x times y is 1. Expectation of x is 0.5. Expectation of y is 1.5. So the product of the two is 0.75. So this is 1 and this is 0.5. This is 1.5. So the covariance is 0.25. All right? And it is positive. Positive means what? Means that for this particular distribution, it seems that if x is above mu x, above the mean, then at the same time the corresponding y should also above the mean, mu y. If it's below mu x, then the corresponding y is also below mu y. Okay, so we work out the variance of x, variance of y, then the correlation coefficient is 0.5774. So it's a moderate. It's not too big, not too small. It's 0.57 or 0.58, all right? If it's 0.95, which means that it's very close to 1, then that means xy are really, really close relationship. Let me ask you. In fact, what does rho xy equal to 1 means? I can give you some idea. So if this is like that, then that means the y and x are the relationships are very strong. That means once you know x, you may likely to know that y. Okay, I cannot say I know the y, but then they are very, very strong associations. Can we say that xy have a very strong association? No, it seems to appear everywhere. All right? But how about if this one? So this one is very close. All the points are very close to a relationship. But this one, the points are not that close, but it still have a positive relationship. This one, the points are almost everywhere. No linear association. So in this case, the correlation likely to be 0. In this case, the correlation likely to be 1. In this case, the value is somewhere between 0 and 1 and maybe close to 1. All right. All right. Conditional distribution of y given x. So we have done this before. So this is the y given x. That means you have to look at John distribution divided by the marginal of y of x equal to 1. So the expectation is 1/4 plus 2 times 1/2 plus 3 times 1/4. So it gives you 2. All right. Now, we have a few more pages. Let me finish this one. All right. So this is the John PDF. All right. And we are asked to find the covariance and also the expectation of y when x equal to 1/2. In order to get this, we need to find the following. You need to find expectation of xy. You need to find the expectation of x, expectation of y. All right? So that this is equal to the difference of this minus the product of these two. For this one, you need to know the marginal distribution of y given x equal to 1/2 and then get the expectation. So these are the steps that you need, or the quantity that you need to find. All right, so I find expectation of xy. So integrate xy times f of xy. I integrate x first. So that means I fix y and then look at the x. So you see this is the range. So sorry, it's like this, right? So for fixed y, for fixed y, x is from 0. For fixed y, x is from 0 up to 1. So the integration is from 0 to 1. That means I integrate this one over this part. Then remember, only integrate with respect to x. So we fixed the y and then integrate x. So all the y are fixed. All right? Oh. Oh, yeah, there's a y there. Okay. Okay, so the answer is 43 over 54. After you complete this one, now then you integrate over y. So after you integrate x, that means everything is condensed on this line. And only this part with non-zero density that is given by this. All right, you integrate and then you got this. Get the expectation of x, get the expectation of y, and the covariance is equal to this minus this. And it's a negative value. It's not wrong, but you can have negative covariance. It simply means that xy goes in a different direction. But judging from the magnitude, it's very small. All right? Finally, get the conditional distribution, and you can get it from this. And the expectation is equal to y times this over this region. Therefore, y is from 0 to 2. Integrate over that region. And the answer is 17 over 15. Okay, so we finished this chapter. And only up to section 2 included in the test. The rest, yeah, the rest is not covered in the test. All right. Right? Section 2. Up to section 2, the John distribution. All right, so remember to go for your test this Saturday, 10 to 11. Where is it? Multipurpose Hall 1. Sitting plan, there's sitting plan, but we are still working on it, and will be uploaded either today or tomorrow. So check before you go.